All right. Well, good morning, good afternoon, or good evening, depending on where you are in the world. And welcome to this learning experience brought to you by AWS and Datadog. My name is Cody, and welcome back to Techstrong Learning. We have an exciting presentation ahead, but before we get things started, I have just a couple of housekeeping notes I'd like to review. First off, we are recording today's session. So if you happen to miss any of our discussion, if you'd like to watch again at a later point, or if you'd like to share with your team, you will be receiving the on-demand via email shortly after we conclude this live session. Now, if you'd like to engage with us, there are a couple of ways to do so. The first and the easiest way is to use that chat tab. Now, you can find that chat tab on the right side of the screen. And whenever you find it, I'd like you to let us know from where in the world you are joining us. If you have any questions, we want you to submit your questions to the Q&A tab. Sending your questions to the Q&A just to make sure that we can keep track of all of them for our Q&A portion at the end. And additionally, we have some support staff here on the call with us to help answer any questions. If you jump over to that handout section, you'll see there are some resources available for download. And before we close things out today, we will be giving away not only two $25 Amazon gift cards, but we will also be giving away a backpack courtesy of, I think it's Datadog. So we'll be giving away two $25 gift cards and a Datadog backpack. So let's go ahead and move into our conversation today. How to improve your database performance with Amazon Aurora and Datadog. And I'm joined today by Varma Gottumukkala, Senior Database Specialist at AWS, and Casey Culligan, Product Manager at Datadog. So Varma and Casey, thank you both so much for joining us today. Varma, do you want to get us started?
Sure. Thank you, Cody. So again, thank you for the introduction. So let's get going. Again, I just want to introduce myself. My name is Varma Gottumukkala. I'm a Senior Database Specialist SA from Amazon AWS, and I live in Dallas, Texas. And then I'll be co-presenting this with Casey Callahan. Casey, do you want to introduce yourself?
Yeah, thanks, Varma. My name is Casey Culligan. I'm a product manager for Datadog, and I work on the database monitoring product. I'm currently based in Brooklyn, New York. Megan, do you want to introduce yourself?
I'm Megan. I'm a product marketing manager over at Datadog as well, and I'll be helping answer any questions around monitoring or Datadog in the chat. So if you have any questions throughout the session, put them in the Q&A and I'll help answer them.
Hello, everyone, and my name is Jose Ramirez. I am working together with the rest of the team, but I work directly with Varma. I will be assisting in the Q&A section. So if you have any questions about Aurora or some of the features, please feel free to drop them in the Q&A, and I can answer those for you from a service perspective.
Awesome. So let's get started. We have a lot of agenda to go through today. So this is the agenda today. We'll first start with the introduction to AWS databases, where we'll talk about all the different types of databases we have at AWS. And then we'll specifically kind of tailor into Aurora. We'll go a little bit deeper and learn about Aurora, Amazon Aurora. And then I'll pass it on to Casey to talk about database monitoring with Datadog. And then we both will be doing demos as well. I'll be demoing Aurora itself, and then Casey will be demoing database monitoring tool. And then we'll wrap it up with some Q&A. But again, as I said, right, as we all said, please feel free to kind of post your questions in the chat so that we can answer them right away. And with that, let's get started. So I would like to start, right, by talking about three major trends that impact the way you think about data. There are three trends, right? There is an explosion of relevant data you could track. Microservices challenges, right? Microservices change data and analytics requirements. And the DevOps model, right? That's what we kind of work on today, is basically drives a rapid rate of change. Again, as you all know, right, there's an explosion of data being generated. You have to track a lot of data that comes from your business applications. However, right, the growth is coming from data generated by network connected smart devices that drive a variety of volume of data. Every smart device produces real-time data, such as your mobile phones, connected cars, etc. By our estimates, right, data grows at around like 10x every 5 years. To take advantage of all of this data, right, you need to be able to partner with someone who can easily harness this volume of data. And organizations are also moving from a development of monolithic applications to a microservices architecture. Microservices architecture, right, lets organizations break down a complex problem into independent units so developers can operate in small groups with less coordination and therefore respond more quickly and go faster. However, right, there are two implications. It means developers can break down apps into smaller pieces and pick the best tool to solve each problem. And it increases the need for real-time monitoring and analytics to understand what's not working between all of the different microservices. And then as we innovate quickly, right, and the velocity of IT changes, businesses are transforming IT to the DevOps model. This model, right, uses automated development tools to enable continuous development, deployment, and improvement of software. It emphasizes communication, collaboration, and integration between software developers and IT operations. It also introduces a fast rate of change. This means as you think about data and designing your data platform, you need to think about the rapid rate of change that occurs through the DevOps model. And the developers today, right, are building highly distributed and decoupled applications. And AWS enables developers to build these cloud-native applications by using multiple AWS services for scale, performance, security, and manageability. And then back in the 60s, right, back in the 60s and 70s, mainframe was a predominant way of building applications. This lasted until the 80s when client server was introduced and significantly changed the way applications were built. Apps started to become more distributed in nature. However, the underlying data model was predominantly structured, and the database was often a monolith. Then the internet arrived in the 90s, and as a result, right, three-tier application architecture emerged. Clients and application code become more distributed, yet the underlying data model was predominantly still structured. And the databases remained a monolith. The thing I like to point out here is, if you think about it, right, for almost 3 decades, people typically built applications against a single database. And that is an interesting data point because if you have been in the industry for a while, right, you often bump into folks whose mental model is, hey, I have been building apps for a long time and it is always against this one database. But what has changed, right? Fast forward to today, and microservice architecture are how applications are built into the cloud. And microservices has finally reached the database, right? And the developers want to avoid a single overburdened database with one storage engine and one compute engine trying to handle every single access pattern. The expectations for builders as well as end users of today's applications is really different from the way it used to be. The latency requirements are much lower, and they are expected to be able to handle millions of transactions per second with many millions of people using the app simultaneously. These expectations, right, have resulted in data management systems with specialized storage and compute layers optimized for given use cases and workloads. This is because developers never has to trade off functionality, performance, or scale based on the database choice. And then there are a number of factors, right, that are contributing to the performance, scale, and availability requirements of modern apps. The first thing is users, right? User growth is a common KPI for businesses, and the cloud's global reach enables businesses to touch millions of new customers. And there is data volume. Your businesses are capturing more data about their customers to either increase the value of their existing products or sell them new products. This results in terabytes or even petabyte scales of data. And these businesses, right, don't want to dilute the user experience in order to reach new markets or grow their customer base. That means they always want performant systems. And then as businesses use the cloud's global reach to develop more interactive user experiences in more markets, they need their application, they need their apps, right, and databases to handle unprecedented levels of throughput. Very rarely, right, one database fits the needs of multiple distinct use cases. The days of one-size-fits-all monolithic databases are behind us. A one-size-fits-all approach of using a relational database as the only store for your applications no longer works. So developers are doing what they do the best, breaking complex applications into smaller pieces and then picking the best tool to solve each problem. This ensures that the applications are well architected and scale effectively. The best tool for a job usually differs by use case. So developers are now building highly distributed applications using a multitude of purpose-built databases. And Amazon.com, right, took this approach when it migrated 75 petabytes of internal data stored in nearly 7,500 Oracle databases to multiple AWS database services, including Amazon DynamoDB, Amazon Aurora, Amazon Relational Database Services or RDS, and Amazon Redshift. The migrations, right, were accomplished with little or no downtime and covered 100% of our proprietary systems. This includes complex purchasing, catalog management, order fulfillment, accounting, and video streaming workloads. We kept careful track of the costs and the performance and realized the following results. We reduced the database costs by over 60% on top of the heavily discounted rate we negotiated based on our scale. Customers regularly report cost savings of 90% by switching from Oracle to AWS. And latency of our customer-facing applications was reduced by 40%. And then the switch to managed services, right, reduced the database admin overhead by 70%. Another important thing is the migration gave each internal team the freedom to choose the purpose-built AWS database services that best fit their needs, and also give them better control over their budget and their cost model. Low latency services were migrated to DynamoDB and other highly scalable non-relational databases such as Amazon Elasticache. Transactional relational workloads with high data consistency requirements were moved to Aurora and RDS. Analytical workloads were migrated to Redshift, our cloud data warehouse. And then, as I mentioned earlier, developers are building highly distributed and decoupled applications. AWS enables developers to build these cloud-native applications by using multiple AWS services for scale, performance, and manageability. AWS takes care of undifferentiated heavy lifting, whereas your developers can focus on building great customer experiences. And many existing applications are built on legacy databases, and customers have had to deal with the old guard databases, providing that old guard database providers that are expensive, proprietary, have high lock-in, and impose punitive licensing terms, and perform frequent audits. For customers running legacy databases, right, and analytics infrastructure on-premise or self-managed in the cloud or EC2, provisioning, operating, scaling, and managing databases, data lakes, search, and streaming services is tedious, time-consuming, and expensive. They have to worry about operational efficiency issues such as hardware and software installation, configuration, patching, and backups. Performance and availability issues, scalability issues such as capacity planning and scaling clusters from compute and storage, and security and compliance issues such as network isolation, encryption, and complex programs such as PCI, HIPAA, FedRAMP, etc. Customers want to spend time innovating and building new applications and not managing infrastructure. With AWS services, you don't need to worry about administration tasks such as server provisioning, patching, setup, configuration, backups, or recovery. AWS continuously monitors your clusters to keep your workloads up and running with self-healing storage and automated scaling, so that you can focus on higher value application development. You never have to over or under provision infrastructure to accommodate your application growth, intermittent spikes, and performance requirements, and incur fixed capital costs, which include software licensing and support, hardware refresh, and resources to maintain the hardware. AWS does it all for you so that you can spend time innovating and building new applications, not managing infrastructure. The most straightforward and simple solution for many customers who are struggling to maintain their own relational databases at scale is a move to a managed database service like Amazon Aurora or Amazon RDS. In most cases, customers can migrate workloads and applications to a managed service without needing to re-architect their applications. And the teams can continue to leverage the same database skill sets. Customers can lift and shift their self-managed databases like Oracle, SQL Server, MySQL, and Postgres, and MariaDB to Amazon RDS. For customers looking for better performance and availability, they can move their MySQL and Postgres databases to Amazon Aurora and get 3 to 5 times better throughput. For decades, right, the only database choice was relational database. So no matter the shape or function of the data in the applications, the data was modeled as relational. Instead of the use case driving the requirements of the database, it was the other way around. The database was driving the data model for the application's use case. Is a relation database purpose-built for normalized schema and to enforce reference integrity in the database? Absolutely. But the key point here is that not all application data models or use cases match the relational model. Developers are building highly distributed and decoupled applications, and AWS enables you to build these cloud-native applications by using multiple AWS services for scale, performance, and manageability. Let's take a look at the database services offered by AWS. I'm not going to kind of go through all of these different databases, but what if we, instead of take the about the common database category, right? These are the common database categories. This is the simple mental model to help us reason how builders use these different databases. We have relational databases, and within this we have Amazon Aurora and Amazon RDS. And then we have a key value database, which is if you need a single-digit millisecond latency, consistent single-digit millisecond latency, we have Amazon DynamoDB. And if you have a document-based data like JSON, we have an Amazon DocumentDB with MongoDB compatibility. And when we have two flavors of in-memory databases, Elasticache and MemoryDB, Elasticache is kind of both are Redis compatible, and MemoryDB is a completely durable Redis compatible in-memory database. And we have a graph database, Neptune, for your graph workloads. And then we have a time series for your time stream database. Data needs, and we have a ledger database for QLDB with QLDB, and we have a wide column database called Amazon Key Spaces, which is Cassandra compatible. So with that, right, let's take a deeper look at Amazon Aurora. Amazon Aurora is a MySQL and PostgreSQL compatible relational database built for the cloud that combines the performance and availability of traditional enterprise databases with the simplicity and cost effectiveness of open source databases. Amazon Aurora is up to 5 times faster than a standard MySQL database, and then 3 times faster than standard PostgreSQL databases. It provides the security, availability, and reliability of a commercial databases at 1/10 the cost. Amazon Aurora is fully managed by Amazon Relational Database Services, which is RDS, which automates the time-consuming administrative tasks like hardware provisioning, database setup, patching, and backups. Amazon Aurora features a distributed fault-tolerant, self-healing storage system that auto-scales up to 128 or 64 TB per database instance based on the engine version. It delivers high performance and availability with up to 15 low-latency read replicas, point-in-time recovery, continuous backup to Amazon S3, and replication across 3 availability zones. So digging into the first point, right, while we are compatible with MySQL and PostgreSQL, we have made a number of changes under the cover to deliver superior performance and availability. We have separated the compute and storage layers. The compute layer includes the query processing, transaction, and caching layers in a traditional database and is marked in blue here. The storage layer is in green. The storage layer is a purpose-built log-structured distributed storage system. It is a multi-tenant and spans across hundreds of nodes distributed over 3 availability zones. You can think of an AZ as a fault-isolated data center. A given Aurora database is split into 10 gigabyte chunks. Each 10 GB chunk is copied 6 times with 2 copies in each AZ. That means anytime you store something in Aurora database, it stores 6 copies of it in 3 availability zones. This sounds neat, right? But what does this buy us? For starters, right, you can lose an entire data center as well as 1 more copy and still be able to recover your database. Finally, you can add up to 15 read replicas that all sit on top of the same storage. And while this may seem unglamorous, one of the biggest advantages of moving to a managed database like Aurora is you get to focus on the stuff that drives your business rather than making sure the machines are doing their job correctly. When you're running your database on premises, you have to do everything yourself. This is all the stuff in white. And then as you move to Amazon Aurora on the right, most of the stuff, all the boxes in green, are managed for you. And you only have to focus on optimizing your application. Let's look at some of the advantages of moving to Aurora. Let's look at backtrack. For Amazon Aurora with MySQL compatibility, there's a feature called backtracking. Backtracking, right, rewinds the database cluster to a time you specify. Backtracking is not a replacement for backing up your database cluster so that you can restore it at a point in time. However, backtracking provides the following advantage of traditional backup and restore. You can easily undo mistakes here. if you mistakenly perform a destructive action such as delete without a where clause, you can backtrack the DB cluster to a time before the destructive action with minimal interruption of service. You can backtrack a DB cluster quickly. Restoring a DB cluster to a point in time launches a new DB cluster and restores it from backup data or a DB cluster snapshot, which can take hours depending on the size of your database. Backtracking a DB cluster doesn't require a new DB cluster because it's backing up the same cluster and revenge the DB cluster in minutes. You can explore earlier data changes. You can repeatedly backtrack a DB cluster back and forth in time to help determine when a particular data change occurred. For example, you can backtrack a database cluster 3 hours and then backtrack forward in time 1 hour. In this case, the backtrack time is 2 hours before the original time. And then there's a zero downtime patching feature that attempts on a best effort basis, right, to preserve client connections throughout an engine patch. If ZDP or zero downtime patching, right, executes successfully, application sessions are preserved and the database engine restarts while patching. The database engine restart can cause a drop in throughput approximately for about 5 seconds. And then there's fast cloning. Using database cloning, you can quickly and cost-effectively create clones of all the databases within the Aurora DB cluster. The clone databases require only minimal additional space when first created. Database cloning uses a copy on write protocol in which data is copied at the time the data changes, either on the source databases or the clone databases. You can make multiple clones from the same DB cluster. You can also create additional clones from other clones. You can use database cloning in a variety of use cases, especially, right, where you don't want to have an impact on your production environment. Some examples are the following. If you want to experiment with and assess the impact of changes, such as schema changes or parameter group changes, you can use the cloning to test it out. And then if you want to perform workload-intensive operations, such as exporting data or running analytical queries, create a copy of the production DB cluster in a non-production environment, right, for development or testing. You can use the cloning for all these different use cases. And then we have Aurora Global Database. An Aurora Global Database, right, consists of one primary AWS region where your data is mastered, and one read-only secondary AWS region. Aurora replicates data to the secondary AWS region with a typical latency of under a second. You issue write operations directly to the primary DB instance in the primary AWS region, and then Aurora Global Database uses a dedicated infrastructure to replicate your data, leaving database resources available entirely to serve your application workloads. Applications with a worldwide footprint can use reader instances in the secondary AWS region for low latency reads. In the unlikely event your database becomes degraded or isolated in an AWS region, right, you can promote the secondary AWS region to take full read-write workloads in under a minute. The Aurora cluster in the primary AWS region where your data is mastered perform both read and write operations. The cluster in the secondary region enables low latency reads. You can scale up the secondary cluster independently by adding one or more DB instances, which are basically Aurora replicas, to serve read-only workloads. For disaster recovery, right, you can remove and promote the secondary cluster to allow full read and write operations. Only the primary cluster performs write operations. Clients that perform write operations connect to the DB cluster endpoint of the primary cluster. And then, finally, right, Amazon Aurora serverless. It's an on-demand auto-scaling configuration for Amazon Aurora. It automatically starts up, shuts down, and scales capacity up or down based on your application needs. Aurora serverless allows you to run your database on AWS without managing database capacity. You are never paying for what you don't use, while still benefiting from Aurora's high availability, scale, and speed. Aurora Serverless V2 was designed to provide full auto-scaling. It can monitor usage and automatically adapt database capacity to actual application loads. So with that, right, that concludes the part of my presentation. So I'll do a small demo of Aurora. So this is kind of the Amazon RDS console, which basically shows I have like two different Aurora clusters here. One is a MySQL cluster. As you can see here, I have a writer instance and I have a reader instance. And I have, again, Aurora Postgres cluster. Again, I have one writer and then two reader instances. There are a number of things that you can do here. For example, if I look at my Postgres cluster, okay, so here I can do a number of things. I can basically create a clone, take a snapshot, or restore to point-in-time recovery. And there's another cool feature where you want to export your data to S3. You can do that as well as the click of button. And then you can add a replica auto scaling, and that you can, for example, right? Let me kind of go through one by one. So here I have like one primary writer and then two readers. I can add additional reader if I think that I need more reads. So here it will basically bring up this screen. I can give it a name, reader 3, and then I can choose an instance shape. For example, if I have some large, maybe I need to run an analytical workload on some instance, I can choose a really large instance and then run it the low workload and then maybe bring it down. And then I can choose this, the instance shape. I can choose all these preferences and I can create a reader. I'm not going to create it, but that's how you can kind of create it. And then you can also take a snapshot of this, similar, like where it will take a snapshot at this time of this particular database. And then, for example, if you see here, right, my demo portal instance 1 USE2C is my writer instance. And if I want to say failover this database, that means that I can initiate a failover. And then what happens is it will basically fail over to the one of these instances. And then here, if you see, my reader 2 is a smaller instance, T3 medium. And then my demo portal PG instance 1 is R6G large instance. So by default, it will choose a larger instance to fail over. So in a few seconds, right, like under 30 seconds, it should fail over and then make my instance 1 as my primary. And then that's kind of the what and then creating a new database cluster is fairly simple as well. If you go to create database, there are two options, standard create and easy create. If you choose easy create, a few options are automatically chosen for you, but I will go through the standard create, which will show you all the different engine versions which you can choose. It will show Aurora MySQL compatible, Postgres compatible, or RDS, which is basically it supports in MySQL, MariaDB, Postgres, Oracle, and MySQL Server. And then here, I can choose the engine version of each database. I can select if I want a production version or dev test version, which basically, right, a production version means that it'll choose a different instance sizes. And then I can give it a name for the database cluster. I basically choose and then again, we can use a AWS Secrets Manager as to manage your the password for this particular database, or I can actually automatically generate a password. And then I can choose between a standard configuration or IO optimized configuration. It depends on the IO you're expecting. And then again, I can choose if you want a serverless or a memory optimized or burst application classes. And then again, there's like a number of options which you can choose now, and you can create your cluster pretty straightforward. I will cancel that out, and then so if you see here now, it's after 30 seconds now. So this instance 1 became a writer now, and then this automatically became a reader instance, demo portal instance, this 2C1. And then if you go to the MySQL, there's additional option here, which basically, right, shows you to backtrack, because this backtrack is available in Aurora MySQL. So you can actually backtrack in time to a certain point of, so I can choose what time I want to backtrack to, and I can backtrack your DB cluster. And it will typically take a few minutes to backtrack. That's pretty much kind of what I want to show. Again, if you have any questions, feel free to post them in chat, and then we will answer them as soon as possible. With that, I would pass this on to Casey to talk about database monitoring.
Thanks, Varma. So now that we have explored the reasons that you might consider hosting your databases with AWS, let's dive into how you can start monitoring them alongside your broader technology stack using Datadog. Datadog is an all-encompassing observability platform that uniquely covers your entire technology stack, including infrastructure, applications, and real user experiences. Our platform is designed to support developers, operations, IT, and security teams, promoting effective collaboration and improvements throughout the software development lifecycle. Let's take a moment to explore some background about our platform. Datadog was founded in 2010 with a mission to tackle unified monitoring of any stack at any scale. Datadog was also the first in the market to unify the three pillars of observability: metrics, logs, and traces. Since then, we've continued to innovate rapidly by introducing new products, as shown in our visual here. What sets us apart is that every new addition is carefully designed to fit seamlessly into the rest of our platform. On this slide, we see a categorized and comprehensive list of all of our products. For today's discussion, we'll be zeroing in on the first two product categories shown on the left side here: infrastructure monitoring and application performance monitoring, otherwise known as APM. More specifically, I'm going to tell you about our database monitoring, or DBM, product offering, and show off some of its current capabilities in a demo. When your journey with Datadog is first starting out, one of the fastest ways that you can unlock value is by using our 600+ integrations, which offer a wealth of metrics alongside out-of-the-box dashboards. As you may know, AWS provides scalable infrastructure through services like ECS, EKS, and EKS blueprints. This added technology can introduce complexity within your company's ecosystem, requiring increased visibility for efficient issue diagnosis. Enter Datadog, which simplifies complex data collection for companies of all sizes and industries, from startups reducing infrastructure costs to enterprises expediting product releases. With our easy-to-use AWS integration, which includes the AWS overview dashboard shown here, Datadog gathers metrics, logs, and tags from over 100 AWS services. To get started, you'd simply install the Datadog agent, a lightweight software that's deployed directly on your on-prem hosts and EC2 instances, or remotely in cloud-managed setups like RDS and Aurora, for granular metric collection, capturing details such as memory usage and disk latency. In short, Datadog is an all-in-one monitoring solution, offering both a high-level overview of infrastructure and application health, as well as deep insights into specific services such as AWS Lambda and EKS. Now that we've discussed how Datadog simplifies complex data collection across your AWS ecosystem, let's shift to better understanding how it addresses your database needs in particular. With Datadog, our database-specific integrations allow you to oversee database health in the same platform as the rest of your technology stack. Begin by exploring our fully customizable, out-of-the-box database dashboards, including the AWS RDS Postgres one shown here. These dashboards provide tailored insights into database performance and metrics that meet your company's unique requirements. Let's now explore Datadog DBM, an extension of our integration capabilities. It offers thorough visibility into the activity occurring on your databases and enables detailed performance analysis down to the query level, helping you identify the root causes of various issues. Before we dive into DBM's specific capabilities, let's first consider why a tool like it is essential. First, issues often begin at the query level. Therefore, having query monitoring in the same platform as the rest of your technology stack reduces the mean time it takes to resolve these issues, which we refer to as MTTR. Second, poorly written queries can generate noticeable load on your databases, resulting in significant costs that can only be effectively addressed through query monitoring and subsequent optimization. Lastly, traditional isolated database tools often lack essential application context required for troubleshooting. You might be wondering to yourself at this point how DBM achieves each of the points identified in this previous slide. At a high level, DBM allows you to quickly troubleshoot database issues by examining load with our active connections chart and identifying query bottlenecks through wait events and blocking queries. It also enables you to proactively optimize query performance by analyzing query metrics and explain plans for the slowest and costliest queries. Finally, DBM encourages effective collaboration amongst coworkers. Our agent only requires read-only access to your databases ensuring security while supporting cross-team database visibility and monitoring. Now that we have a better understanding of what DBM does, the last things we'll touch on before the demo are setup and supported databases and hosting types. DBM today allows you to monitor your Postgres, MySQL, SQL Server, and most recently, Oracle databases. Importantly, DBM supports both self-managed and cloud-managed versions of these aforementioned database types, including Amazon Aurora, RDS, and EC2. Before we jump into our demo environment, I'd like to highlight this visual that provides an overview of setting up Datadog based on the Amazon technology covered earlier in this webinar. For cloud-managed setups like RDS or Aurora, install the agent on a separate host and configure it to connect remotely to each managed instance. DBM will then gather system metrics like CPU, memory, disk usage, logs, and other related telemetry directly from Amazon via Datadog's integration. Now let's see DBM in action. Resolving issues with databases can be complex and timely. During your investigations, your business may experience consequences like reduced performance and the risk of severe data loss, which can significantly impact your ability to operate. Given this possibility, you need a tool that can help you quickly understand how the databases that your services depend on are running and be able to troubleshoot issues when they arise. With the DBM view we see here, which we'll refer to as the databases list page, you can quickly assess the overall health and performance of your entire database fleet for effective real-time troubleshooting. The supported database types referenced earlier in my talk are displayed here. Remember that we support both self-managed and cloud-managed versions of these databases. One way to kickstart your troubleshooting in DBM is through our high-level Watchdog Insights. This feature serves as an excellent starting point for investigations, as it allows you to filter for specific weight group anomalies, such as CPU, network, or idle. These weight groups represent different events, or rather different resource categories that could have impacted one of our hosts shown here. These cards help me quickly find databases with interesting activity, making it easier to identify potential issues. To get started, I'll select this AWS RDS host with abnormal idle weight group activity. And with just a few clicks, I can learn more about what the idle weight group is, investigate the top queries contributing to this unusual weight activity, and review the active connections on my database at the time that it was detected. Watchdog Insights are just one way of identifying interesting activity within our list of databases. We can also leverage the active connections, or load chart, to help us pinpoint misconfigured or problematic hosts. Active connections are sessions running queries on each database displayed by DBM. These connections can either be actively processing or waiting for specific resources like CPU or memory. Let's pretend that I'm a database administrator or a DBA. As a DBA, my daily routine might include thorough health checks to ensure the optimal performance of my company's SQL Server production instances. While looking at my instances, I noticed that this AWS RDS host has a substantial amount of active connections. I know from my experience as a DBA that too many active connections can overload a database, potentially resulting in blocked queries. This blocking in turn could cause widespread issues for the services attempting to access this database. So I'd better take a closer look into what's going on with these active connections. When you click on any host in the databases list page, you get more detailed information about the activity happening there, which is essential when trying to identify any events affecting performance. This Active Connections by dropdown offers multiple ways to analyze the sessions data collected by DBM. By choosing the wait event option, I can see the wait events that are most common for this host. Wait events are a more specific classification than wait groups, as they pinpoint precise causes of delays in the database, while wait groups offer more broader categorizations. This breakdown of wait events helps me understand where queries are spending most of their time. In this case, the waiting on CPU wait event suggests that the server's CPU may be overloaded, leading to competition for processing time among various queries and tasks. It's worth noting that this host also is sometimes coming close to its vCPU limit, as indicated by this red line here. This indicates that the host's processing capacity is periodically under strain. Let me check the metrics tab quickly to see what other information is available to help aid me in my investigation around this host. Interestingly, I see CPU usage is on the higher end, but it's not quite maxed out or at risk of being maxed out. This is useful information, but I want to understand more about how to ensure the queries running on this host aren't frequently waiting on CPU resources to be able to run. I'll switch to the blocking queries tab to see how the queries running on this host are impacting each other. Note that my previous time range was 1 day, but there was an activity to report then, so I went back a week in time. I also adjusted the active connections chart to show me only lock wait group activity. At the aggregate level, this blocking overview tab, we can switch between viewing the queries causing blockages and those that are waiting to better understand how blocking occurs and which queries to address when mitigating the impact of root blockers. We can also see individual blocking events with associated blocking trees that depict the breadth of impact of our root blockers. This view is especially useful in more live troubleshooting scenarios, as with the information shown here, I'm able to determine any significant blocking events happening in near real time, measured by a variety of factors such as block duration and number of waiters. These blocking events are indeed interesting, but there's no immediate real-time blocking happening. It's evident to me that the more pressing concern within this host scope pertains to CPU resources. So I'll adjust my approach and focus on examining the top queries instead. Looking at the top queries tab, I can see which queries are contributing the most to the load on this database, in addition to a query-specific breakdown of the resources that each of them are waiting on to run. Note that these statements are displayed as normalized queries, which are a set of queries with the same structure, but different values for the parameters that have been grouped together. Note that these parameter values have been obfuscated to hide confidential information or personally identifiable information. We also display information about the individual query executions in a different part of our product called query samples, which we'll peek at shortly. By clicking on any of these statements, I'm brought to the normalized query panel. Within this view, I can gain more information and data around the query, such as average latency, total time, and requests. We can even see within this panel that this query could benefit from an additional index or two. To better understand, though, why these indices were recommended, let's check out the explain plans that we've collected for this query. To clarify, when we say explain plans, we're referring to the different steps that the database takes when it goes to run the query. Typically, I'd need to log into the database and actually run the query to get this information. The data that I'm seeing here indicates that a couple of different explain plans are run for this query over time, one of which seems to be more costly than the other. This is a signal that I should perhaps rewrite the query to reduce the chance that this costly plan gets executed and measure the subsequent effect that this modification might have on the CPU wait group activity. I'll use the above recommended indices to assist me in rewriting it. When making a change of this nature, it's important, though, that I have a solid understanding of when this query is using each of these explain plans. So I'll click Compare Over Times to help me see just that. This view, which shows me how the explain plan signature and its associated cost changes over time, can assist me in understanding its behavior long term. More specifically, I can come back to this view once I've made my optimizations to monitor how this query performs in the future. I'll click on this explain plan signature that's obviously more costly than the other and view its associated events. And look, I see those same index recommendations that were shown to me previously in the normalized query panel. I'm now in an area of DBM when I can find out more details about the individual executions or query samples associated with this signature. This panel shows me details such as the client IP, user, and even the calling service responsible for this query execution, which is pulled from our application performance monitoring or APM product. In conclusion, with DBM, we were able to identify a database with high load using active connections and wait events, and view contributing factors by looking at our top queries, metrics, and blocking activity. We even identified indices that we could add to one of our top load contributing queries to potentially make it run more efficiently. So as we've seen today, Datadog DBM can help you gain greater visibility into the activity happening across your hosts, as well as identify specific troublesome queries that could benefit from optimization. We designed DBM with best practices in mind to help your teams effectively monitor their databases. To summarize what we've been discussing today, here's what you'll be able to achieve by using Datadog DBM. Visibility into exactly where your queries are being run, telemetry straight from the source, i.e. the database, collaborative and secure monitoring amongst the app developers, site reliability engineers, and database administrators within your organization, and finally, monitoring that's seamlessly integrated with the rest of your technology stack, allowing for more simplified investigations. If you're interested in getting started, we recommend that you try out Datadog by visiting our website or kickstarting a 14-day free trial, both of which are linked in the resources section of this webinar. I now want to thank you for your time and for listening to both mine and Varma's presentation. We hope that you learned something new today. Please continue to submit any questions you may have in the Q&A area.
Perfect. So it looks like we have been receiving some questions throughout our program, and our support has been absolutely stellar with being on top of them. But let's go ahead and bring them into our conversation today. So the first question that we received was, for global databases, will it be synchronous or an asynchronous replication?
So I think that was already answered. So basically, it's a global database is an asynchronous application, and that's basically, I think Jose put in a link to a documentation that kind of explains that as well.
Perfect. A question that we just got in, what are the features and perimeters included in APM?
There are a bunch. I think it'd be best to link some documentation. We could do an entire webinar just on that product, but I think the main appeal right now of APM is that you gain visibility into all of your services that you've configured with the product, as well as all of the requests, errors, etc., that are associated with those services. And we even offer you a breakdown of each of those individual request traces, so you can understand where requests are getting stuck and things that might be contributing to people not being able to access your applications consistently. And I'll also plug the APM DBM integration here. I highlighted it briefly in the query samples view, but we're able to now integrate telemetry from APM into DBM and vice versa, so that you don't have to context switch as much to try to understand whether the database is the main contributor to the request taking a longer time to execute or failing, or any issues that might be happening.
Wonderful. And it looks like the last question that we've received so far is, what type of logs systems are captured, and primarily looking at the database security aspect.
Sorry, can you say that one more time?
What type of log systems are captured?
Oh, okay. I think Megan answered that, but I can just read her response. So Datadog can collect logs from your infrastructure, applications, and more sources. Megan links some docs there that I think would be useful to check out because, again, there's just such a wide range of functionality and places that we pull from that I think it's best to review that material offline.
Awesome, absolutely. So what do y'all see as kind of the number one issue in database performance? What do you see as the most common need for implementing these changes?
I think I caught it a little bit. They were asking about like the key contributors to database performance issues. I think something we see commonly within DBM is that it can come down to like specific query statements, which we show you with our query metrics tab, our normalized queries. We're showing you more aggregate statistics around like which queries are scanning the most rows in your tables and taking the most time to execute, and which ones are just even being executed the most frequently. So we show you that at an aggregate level, in addition to being able to drill down deeper into specific executions to say, was there one particular user or database or client IP that I'm seeing this particular performance issue within? The answer is most likely yes. Sometimes the issue can be very isolated. And so having a tool like DBM allows you to follow that path down to the point where you know who you need to reach out to within your organization to try to get that query optimized and running effectively. So yeah, in short, I would say problematic queries are probably the biggest, one of the biggest causes to performance issues in databases.
And then to add to that, right, at least what we have seen, at least we work with customers like every day, what we have seen is like the data model, choosing the correct data model is very, very important. And then choosing a bad data model basically contributes to a lot of issues, what we see with the customers. And then not choosing the right database for the right use case is also, if you're trying to fit in a particular database to every use case, that will cause to you to over engineer and then cause issues as well. That's something at least we observe every day.
Awesome, thank you. So one last question before we kind of wrap things up is, how can one get started?
So with Datadog, you can feel free to just look us up and look at our corporate website to sort of browse the broad range of products that we do offer. But to get started with DBM specifically, we've included a free trial link in the handouts section. Definitely the best way, I think, to learn about what our tool can do, because I didn't show everything today, is try it out yourself, go through the setup process on your own host, and of course, give us any feedback that you have along the way. So yeah, that can be found in the handouts section.
And then for AWS, again, we offer a number of services that are a free tier. That means that you'll never get charged for those services. And then again, you can create a free account in AWS. And then if you stay within that free tier limit, you can use them as long as you want. It's primarily intended for learning purposes. So, but again, I sent a link in the chat window that will show all the different categories of the free tier services we offer and the limits for those as well. So please take a look. Then yeah, happy learning.
Awesome. Well, Casey and Varma, thank you both so much for joining us today on Techstrong Learning. It looks like we've exhausted our questions, so we're going to give everyone a couple of minutes back and wrap things up about 4 minutes early. But Casey, Varma, again, thank you so much. And to our support staff, Jose and Megan, thank you so much for your help with answering all of our questions today as well.
Thank you so much.
Thanks, guys. Take care.
So I'd like to remind our audience today that this session was recorded. Following this program, you'll receive an email with a link to access that recording on demand, or you can find it living on the DevOps website. That's devops.com/webinars, and you'll find it in the on-demand section. The two winners of our $25 Amazon gift card drawing are Rachel G and Leonardo J. So congrats to our two winners. We'll be reaching out to you via email to distribute these gift cards to you here shortly. If you don't see an email from myself, check your spam folder just in case it happens to be filtered out. I'd like to thank AWS and Datadog for sponsoring our program today. And to everyone here, thank you so much for joining us today. At the top of the chat is a link to our survey, and we would love to hear your feedback, whether it's about today's program or maybe upcoming topic suggestions. Let us know there. We would love to hear. Also anticipate an email from Datadog for one of you, one lucky winner who will be expecting a backpack to be coming your way soon. And I'd like to thank everyone for being here. So you may now disconnect. And to our speakers, Casey, Varma, I really appreciate your time today.
Thank you.